Um, has anybody started this? Anybody want to talk about how they started? Anybody want me to shut up for a few more minutes so they can actually do something? What works here?
Well, I don't know the others, but I'm just starting to this thing, so I may need some time in order to advance with this.
Could you perhaps remind me what the function was to plot membrane potential?
So you construct, you use a range var plot to it's the object, and you say range var plot v and the string v, and then the starting point, the ending point, and then it's rvp.plot, and then you pass in plotly, let's say, and then it'll plot it.
Yeah, thanks. I forgot the name of the plot.
Okay. Because I guess what I'm hoping is you guys can do it a little bit, and then like we talk through it or something. Does that sound like a decent plan? So okay, I will leave you alone for a couple more minutes yet, and then we'll start talking through it. At the very least, try and figure out a plan as to how you would approach the problem if you don't get it all done. Okay, maybe for the first one, we should not spend too long not talking to each other.
Okay.
It's gonna make me angsty.
All right.
So let's let me share my screen for a moment. Okay. Okay, so the instructions say to visualize a propagating action potential with Hodgkin-Huxley dynamics, trigger your action potential using current clamp, plot membrane potential versus position at several time points. And so my suggestion to you is to use Google Colab just because it has everything and it works. Hopefully by the end of this course, if you don't already have it, that'll be true for your computer as well. But so, okay. So everybody could open Google Colab. All right. All right. Cool. So what do we need to do in Google Colab?
First,
Install NEURON first.
Yeah, we're going to need that.
So,
exclamation mark, pip install NEURON. And it's going to spin for a little bit, and it's going to do its thing, but, you know, and it's going to install NEURON. Cool. Yay, that was fun. All right, so far so good. What's next?
import NEURON.
Import
Well, we don't
NEURON.
really import NEURON necessarily. Yeah, NEURON itself is actually not that useful. But we want to grab something from NEURON.
Import.
Yeah.
Yeah, so from NEURON,
Yeah,
let's import H. Let's get H. While I'm at it, I'm just going to go ahead and grab units because I like to use units. Not always perfectly consistent, but it's good to use units, and it makes your code more readable. I'm going to usually want to do a standard run system. So I'm just going to go ahead and let's say I'm going to load std_run.host. Okay. So cool. So far, so good. Very formulaic, but that's okay. We're going good. We're going to want to make a pretty picture. I suggest using Plotly for making our pretty picture. So let's import Plotly. Okay, that was easy.
Sorry, I just reading again the slides. Why isn't not advised to use Matplotlib?
Oh, because Matplotlib and okay. Plotly lives in your web browser, basically. And so it's going to be much more responsive than Matplotlib graphics. That's all.
Okay, thanks.
Yeah. Okay. But yeah, you could use Matplotlib if you wanted to as well. Okay. So we've loaded some libraries. All right, cool. Visualize a propagating action potential with Hodgkin-Huxley dynamics. So what are we going to need if we're going to have a propagating action potential?
Axon.
Let's have an axon. I like that. All right. Axon is an h.section. I will give it the name of axon.
Yeah.
How long should an axon be?
According to this, should be like 1 centimeter.
1 centimeter? Could do that. I could, you know, if I want to make sure that I have something that I can really see, let's go even, let's be, yeah, 1 centimeter, really. Okay, fine. You want 1 centimeter? We can do 1 centimeter.
Well, the slide says at least no, it's 1 millimeter. Sorry. Yeah, 1 millimeter.
1 meter is very long. Let's do 1 centimeter. That's still pretty long.
Yeah.
Right?
Yeah. Sorry, just got the makes it.
All right. So my axon's going to be 1 centimeter. Okay. It should have a diameter. What's a good diameter? 1 micron. Cool. Glad we came up with that together. Okay, so I have an axon. It is long. That's fine. What is that in microns? That is 10,000 microns. It is very long. But there we go. We see an actual example of using units for something non-trivial, right? We entered it as 1 centimeter and it turned it into microns. Cool. We're going to need to do a couple of things in order to get a propagating action potential. What do we need? Biologically, what do we need?
Channels.
We need channels. All right. Hodgkin-Huxley?
Sure.
Yes.
Why not?
H.HH. We're going to insert those into the axon. All right. There's something else that we're going to need to get a propagating action potential.
Yeah, the stimulus.
What's this? Oh, we're going to need a stimulus. Okay. So I said a current clamp. So let's make a current clamp. If it's going to propagate, let's start it out at the beginning of the axon. So we're going to create a current clamp. It's going to be started at the beginning of the axon. It's going to have, current clamp has a few properties. It's got a delay, it's got a duration, and it's got an amplitude. Delay is the time that the current clamp starts. I don't want to start at time 0 or I won't be able to see the difference between, I want to be able to see that the cell's at rest before it does something, right? So when should we start?
5 seconds.
5. All right, cool. I like it. This is in milliseconds, but I'm going to be lazy right now. How long and how much current should we inject? Anybody have any intuition?
No.
Well, there's an example from the website where it has 0.1 for duration and 0.9 for amplitude.
All right, cool. I have no idea what example you're referring to, but cool. That's fine. Something will happen. Remember, this is the great thing, right? We can't kill ourselves. So if we're inputting too much, it's not a problem. Just rerun. If we put too little, it's not a problem. We'll just rerun. It's pretty much a win-win. Okay. So we've got a current clamp. We've got our ion channels. What else do we need?
Want to record
well, we don't actually need to record it per se, but we are going to want to create a plot, right? We're going to want to do a plot. So let's say, so we're going to have a range var plot. I like to call it range RVP, but that's just because I'm lazy. It's a mnemonic. It helps me remember. I'm going to trace the voltage from the beginning of the axon to the end of the axon. That's going to be the thing that I'm going to use to plot. Okay?
Okay, so this range var plot, how many subdivisions is going to take into account?
Ah, that is an interesting thing. Talk to me about subdivisions. Talk to me about segments is the word I'm looking for.
Segments.
Talk to me about segments. Why do segments matter?
Because if not, I am not going to have any convergence in the middle. Not convergence, but I'm not going to have any data in the middle.
Well, I've got a thing that we said was 10,000 microns long. And by default, since I haven't told it to do anything else, there's only one segment, which is to say that there's one numerical compartment. Which means that if I were to plot it, I'd have one number. That's not going to show a propagating wave because that's only doing it at one point.
Okay.
So we're going to need to break it up into a number of segments. For our purposes, I don't think this is going to matter that much, but we have a really long axon, so we ought to have a fair number of segments. 1,000?
Could you maybe,
yeah,
since you mentioned it in your talk, show us how whatever, was it a module that basically does all the computation for how many segments you want for you?
No, because I don't remember how to do it, which is why I paused.
Well, we can postpone.
It's a library. I will put it on Slack. I promise. But for our purposes right now, let's just go ahead and add something. And I like to group everything together, so I'm just going to add it up here. It really doesn't matter what order I do it in. But let's say I'm going to say that it's going to be broken down into 1,001 compartments, one for each night. But why did I make it 1,001 and not 1,000?
So you've got one in the middle?
So I've got one in the middle. It's an odd number. It's really just use odd numbers. It's better.
I'm sorry. I'm facing a problem here in action length. The type error is unsupported operand types for asterisk. Don't know why.
This line?
Yeah.
In axon.l, in action length.
Axon.l, and you set it equal to what now?
Unsupported operand types for asterisk.
What is on the left side? What's on the right side? What do you
Sorry? I didn't hear you.
Oh, so here I have axon.l is equal to 1 times cm.
Mm-hmm.
That's what you have?
Yeah, exactly the same.
Did you import the centimeters from NEURON units?
Yes. All of them, as I can see.
Right.
Yeah.
So if I just print out cm, it should be, cm is literally the number 10,000. What is cm to you?
Let me see. Oh.
I'm going to go with something else.
Yeah, let me check again.
So my
module matplot no, I didn't get the same result. Don't know why.
Anybody else having that issue?
So if you ran
Sorry?
the cell that had all the imports and then you added CM after, you have to rerun that cell.
I solved it.
Okay.
By mistake, I had import matplotlib from matplotlib import SM. So yeah, my bad.
Okay.
Sorry.
Yeah, no worries. I'm going to just get rid of that line just to keep my story clear. So I'm going to create a range var plot. We've said that we're going to have, did I actually run that line? Yes, I did. We said that we're going to have 1,001 sections. And then now we've basically defined everything, right? So let's initialize. How do I want to do this? Okay, I'm going to initialize. Let's just say to -65 millivolts. It's as good of a thing as any. And I want to plot this out at a bunch of times. What time should I plot here? Maybe once. Let's do it once and see if I have it working at all once before I try and do it several times. That sound good? Always do something, don't jump into a big thing until you get the simple thing doing. So
we're not recording anything yet though, right?
We're not recording anything at all, actually, in this process. We don't need to for this one. Because all we're going to do is we're going to run it a little bit, and we're going to plot it, and we'll run it a little bit longer and plot it, and we'll run it a little bit and plot it. That makes sense? And I don't know why VirtualMarks just launched.
Because we don't need a time recording, no?
Not for this, because I'm not looking at one point. So if I was tracing the trajectory at one point, I'd want to store the voltage at that point and the time that I was recording. But here, I'm actually I'm going to plot at specific known points and at known time values. I'm going to plot it across position. So I'm plotting the entire axon at one time.
But in theory, I could insert like 1,001 points of recording and then just have it run for what, like 5 milliseconds, and then
yes. Okay. If you wanted to do that, you could do that, and then you'd have every location's value at every time point, which is kind of cool, but it's a lot of data. But so before we try and do more than one, let's do one. So we know we said that the current clamp was going to happen at time 5. Okay. So let's say that I run it until 6 milliseconds. And then I will plot this, rvp.plot. I'm just going to throw it on a plotly, and I'm going to show that sucker. And let's see what happens. It's an experiment. Okay. Maybe. It got up to -53. What do you think? Is that going to make an action potential, or is that not going to be an action potential?
No, that's not.
Let's run it a little bit longer just for kicks. I'll run it to 7, and I'll plot it. Oh, it got to -35. I'm betting that's going to work. Let's go to 10 and plot it. Look at that. So now we have an action potential. It's a funny looking action potential because we're probably used to looking at it at one point, but this is how it looks as along the axon. Does that make sense?
Mm-hmm.
And then if I would have run this a little bit longer, it's a very, we started out with a very long axon, so this works to our advantage. We can run it for a good while, and now here it is at 20. And clearly, it's the same thing, but over there now. All right, so we have a propagating action potential. So it works. So how do we add? So then the actual task was to plot a whole bunch of these on one graph and just sort of show the evolution. So let's just do this. Anybody want to tell me how to do this?
A for loop.
A for loop. All right. So let's just say I'm going to go put it here. So for let's say t-stop in, what do you think? Range of 5 to 25.
Mm-hmm.
That's a lot, isn't it?
Yeah.
We'll plot half of it. What do we do? Well, for each of those values, I'm going to run it that far. Right? Yeah. So there's one minor little obnoxious thing here. So rvp.plot, if I pass in plotly every time, it's going to
create a new one.
Yeah, so that's not quite what we want. So the way we do this is I'm going to start out with the original figure. It's just going to be plotly, let's say. And then I'm going to update it every time. So I'm going to plot, I'm just going to pass in the plot. It's going to overlay it, and then it's going to store that fig. And it's going to do that again and again and again. And then when all is said and done, I'm going to show it.
Mm-hmm.
And if we're lucky, so this is, by the way, this is a little bit wonky. There's a little bit of extra logic here. This is why it was really good that we tested to make sure that we actually had an action potential. So we know that it's going to work if we do this part right. So now we got to find out if we did this part right. It's an experiment. All right, look at this. So this is trace 2, this is trace 3, this is trace 4, 5, 6. So at each subsequent time point, we got further and further down. All right, looking good. One minor comment here. These are absolutely terrible names, trace 9, trace 6. So then this is where I like to say, so any argument that you can pass to plotly, you can pass to rvp.plot if you're using Plotly. If you're using matplotlib, any argument that you pass to matplotlib, you can pass to rvp.plot. See how this goes. So in particular, in Plotly, if I want to give something a name, it's the variable name. So let's just say that I want to give it a name that's the, let's say t equals something, right? And if I want it to be t equals 5, t equals 7, t equals 9, how am I going to get that out of there?
F string.
An F string. All right. So it's an F, and then a string, the quotation marks, t equals, and then let's say curly brackets, t stop. Oh, well, I bet that was done on purpose earlier. As an example. So now let's run it. And look at that. We've got the color codes match everything. I can mouse over it. It tells me that this is t equals 13. This is where it's t is 15. And so forth. By the way, if you're not familiar with Plotly, I can always double click on one of these guys to just zoom into that one only, or I can single click to turn one on and off. Fun things that you can do with graphics in the browser. All right. So that was it. That was our experiment. We got a pretty nice thing. We see a propagating wave. You see that's very stylized, right? It looks the same to the left as it does to the right. It moves along, and that's what we expect from an action potential, right? It's got the same dynamics everywhere. It's going to pass, propagate perfectly consistently, and it does. So that's good.
Lord?
Yes, sir.
In case of efficiency, which is better, to plot like we did it here, or just to run the whole simulation, save that vector, and then go and plot each chunk of the vector?
It's not actually like, it's not sending any data. I think it's effectively the same, because it's not actually plotting. It's not actually plotting until you call the show. Right, so it's just building a data structure.
Yeah, that's the point. I mean, you store in memory the figure with every single line. That's my question. Instead of having the whole vector saved and then just get each chunk of the vector. I don't know. Perhaps in this example it's just meaningless, but in a bigger simulation,
the figure is just data. It's not like you're storing pixels. It's not. You're storing. The only thing that's being stored is the data.
Okay.
Could you show your iClamp settings again? I'm looking at my plots and they look slightly different. Oh, okay. Okay, my numbers were a little.
Oh, yeah. Well, I mean, yeah. If your numbers are different, it's going to be slightly different. And cool. So here's a question. So the second part of this said, so the reason, by the way, so this one I used 1,000 microns. Ours is 10,000 microns, and that's why we see the sharper thing. If we had done a different diameter, we would see something different. If we had done, right, all of these things. And so I said, well, okay, so this was with the squid and the squid's axial resistivity. And I said, do the same thing, but with RA is 100 ohm centimeters instead of 35.4, which is squid. So this is the beautiful thing. Here's what we're going to do. We're going to copy, paste, and then we're going to make one little itsy bitsy change. Axon.ra is equal to 100. Let's see what happens. The only thing that I did was I changed the axial resistivity. So, somebody tell me what happened. And better yet, tell me why.
Now they have the hyperpolarization on property.
I'm sorry?
Now the PA have the hyperpolarization property because they have this resistance to despair.
Yeah, so there's a higher axial resistivity which is to say that it's harder to go down the axon, which means that it goes slower because it's harder. If I were to make the axon bigger, a bigger diameter, what would happen?
We'll go faster again.
It would go faster again. Let's try it. Axon.diam equals 2. I don't know. So right now, how far did it get? It got to about 6,000 microns out. Okay? Let's see what happens. If the diameter was, oh, what happened?
We never got an action potential?
We never got an action potential. Because it's bigger, so it takes more to get going. So, okay, IC.amp, let's be crazy. This is a lot of current, but it's not going to kill our cell because it's not alive. Oh, I didn't call it I didn't call it iClamp. Okay, so slightly less dramatic than if it had worked the first time. But there we go. So now we had to inject more current because it was bigger. That makes sense. But once it got going, it travels at a constant rate, but in particular, it traveled further than it did when the diameter was 1. And that makes sense. Any questions about any of that?
Just sort of technicality about this this type of plot. The sampling rate, is that depending on how many segments I divided my section?
Yes.
Section.
So the
if
number of the X resolution is equal to the number of segments.
Okay, so if I had whatever, like 10, it would look really clunky.
Let's find out. It's an experiment. Axon.inseg is equal to 11. I'm going to pretend you said an odd number. And nothing happens. Why is that?
We kind of missed it.
Well, it makes everything be a one really massive compartment. And so I think getting that entire compartment above is going to be... Okay, now I don't know what's going on.
Did we just miss it, maybe? Right? If we just sort of happen to, sort of measure... No, hold on, that doesn't make any sense.
Do we need to update RVP?
I wouldn't think so, but it doesn't seem to be. Oh, maybe we do. It would. I'm gonna guess that that's right. When I've changed the discretization, I bet it broke the pointers. Let's find out. Yeah. Okay. So there with 101, it's a little chunky. If I dial this down to 11, it's a lot of chunky. And then once it gets too low, it's very hard for it to sustain an action potential because they're very large and far apart. Remember, this is 10,000 long, so this is 1,000 runs apart. These compartments are a little too coarse. But maybe 51 would show us something. Yeah, there you go. So now we have slightly chunky action, but slightly wonky. But does that answer your question?
Yeah, thanks.
All right.
And so does this always use like the middle of the segment? That's where
Yes.
it like records from? Okay.
And by the way, so yeah, go ahead.
Oh, I was wondering, can you specify like if you want it to record like 3/4 of the way down instead of like in the middle of the segment?
So the segments, no, is the answer.
Okay.
So a section, I mean, we're recording all throughout the section. We're hitting all the segments within the section. But the segments are always, by definition, the node is in the middle of the segment. And there's a RVP dot, okay, what do we have? This is 2 vector, that sounds promising. Oh, let's see, I don't remember. Yikes. RVP.vector. What's a list of RVP.vector? Okay. Yeah, so these are all of the membrane potentials along the path. And so forth. So you can always go back and get, like, it's not, we're not just making a pretty picture. We can get the data. We can do that.
Could we maybe, for the fun of it, just plot the, try a 3D plot with the membrane potential?
Membrane potential versus what?
Just, along the, the
Oh,
neuron.
you want like the shape plot?
Yeah, exactly.
What do we actually have right now? So we've got it should be non-uniform, right? Because here's where we're at, the yellow one. So let's see what happens. PS is going to be h.plot shape. Nope. Depends if you can spell it. We're going to plot the variable. Nope, that's not how you use plot shape. Why am I having a blank? Do I just pass false? Let's say I think I just passed false. And we're going to plot, so on that plot shape, I'm going to plot the variable v, and I'm going to scale it from, I don't know, -65 to 30, apparently, millivolts, and I'm going to plot it on the plotlet. Let's see what happens.
Yes.
Let's see what happens. What am I doing wrong?
You have to put the dot show after plot.
Oh, for God's sakes. There we go.
Neat.
There is our line, and there's the spot in the middle. Thank you, Catherine. There's our line, and there's a spot in the middle where the membrane potential is elevated, and then it drops back down. And then we're free to spin it around, but there's not a whole lot to see because it's a line in 3D space.
Cool. Thanks.
Yeah. Any other questions on this? All right. I will share solutions to all of these, but we've got. I'm not sure that we can get through all of these before 7, which was the promised end time. It's been a long day for, I think, everybody. Is there something? So we've got a voltage clamp experiment. We've got something looking at the speed of wave propagation. And we've got a full cell morphology. What's most interesting to people? Or I can talk about other things. I like to talk, but
I mean, I would prefer to go with the morphology, and then I think that's easily expandable, right? So whatever, you do that, and you can start inserting synapses and whatnot. So maybe that's something to build on.
Okay. Hearing no other opinions, let's do that. Okay, so here we go. We've got, it says load the standardized morphology from, here's a URL, tinyurl.com, neuromorpho C91662. I am at least consistent. Let's see if it works. Hey, look, there it is. In particular, if I were to do this, here is my, what I did was I clicked the morphology file standardized. And so this is the morphology file. The way you read this, I mean, you don't need to read it. The computer reads it. But if you were curious, this is an X value. This is a Y value. This is a Z value. I never remember if this is diameter or radius, but it's one of those things. And
it's diameter.
It's diameter. All right. Somebody sounds confident. So here we go. here's our file. So let's go ahead and take this. There's the URL. I just grabbed it, copy paste, and let's go to Colab. Boom, colab.research.google.com. All right, let's make a new notebook. I said, let's make a new notebook. Let's do this. Uh-huh. This has nothing to do with NEURON, just for the record. This is entirely. Hello, can we please have a new notebook?
Right.
Is it not cooperating for anybody else, or is that just me? Ted. All right, there we go. Where is it? Where else? I have a new notebook. Yay. Okay, so I'm going to want NEURON. Well, that's easy. Exclamation mark, pip install NEURON. If you're doing this on your own machine, you'd obviously only have to install NEURON once, but whatever. It takes 3 seconds or whatever, so no big. I want to grab that URL that I found, right? I want that locally. So one way of doing this is to use wget. You guys know wget? Yeah, okay. So wget's going to grab that file and save it locally, hopefully. So saving to c91662.cmg.swc. We can check this. I can pop open my file folder. There it is. It's there. So, okay, so I've downloaded a file. You could do this with Python using the request module, but this is not that way. Doesn't matter how you get it. The point is to have it. All right, so this then being the case, what do we need to do next?
All the imports.
All the imports. All right. That's okay. This is rather formulaic. From NEURON, import H. From NEURON dot units. I don't know. No, I'm going to do it because it's a good thing to do. Millivolts. I don't know what I'm going to need. Milliseconds, microns. If we need something else, we'll get that. I'm going to want to make a pretty picture, so I'm going to use Plotly for it. Oh, standard run, right? H.load file, std_run.hope. Cool. So I have all of these things. What? Oh, you know what else? What the big one is that I didn't do? What didn't I load for importing my 3D geometry? My library for importing my 3D geometry. So it's 3D. Nope, that's not how you spell it. 3D. Okay. So I've now loaded my library. Awesome. I'm going to need a place to put my cell. I'm going to suggest that since you're all Pythonistas, let's go ahead and write a class. We don't have to. When I originally did this, I didn't. So this will be fun. But it's good practice to create a class. So class of, no, let's not call it cell. It's a parameter cell. We know what it is. Let's call it parameter. Let's give it a meaningful name. And then here's what we'll do. So we'll create an init, which is the constructor. Takes self by convention. And I'm going to do, well, all right. I like to say load morphology as its own separate function. And the reason being, if I decide to do something else, then I'll be like, and discretize it, and blah, 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 and blah, blah, blah. But so let's do this. So I'll have a thing called load morphology. Yep, okay, cool. It's going to take self. In any case, punchline is I'm going to need to load it. It's going to be very formulaic. So this is going to be cell is going to be h.import. See, here you go. You start typing it, and this is another reason to use like Colab or IPython, right? It's if you forget what these things are. But see, I told you there was eutectic. There's NeuroLucida 3, there's good old NeuroLucida, but we want SWC. So we're going to import, we're going to load our reader. We're going to input the file. Yeah, remember it came in a C91662 dot capital C and G. Don't know what that stands for, but that's fine. Dot SWC. We're going to create this guy, import 3D GUI. We're going to pass in the cell, and we're going to say false. And then we're going to instantiate this inside this object.
So am I correct that basically instantiate then associates a bunch of, well, I guess some sort of variables with the class itself, right?
Absolutely. So let's try it. This is how we find out, right? So we're going to create a pyramidal cell. I mean, I haven't put any ion channels in here, but I'm going to go ahead and try it anyways because I can do that experiment because it's in the computer. So I create a pyramidal cell, and let's just look at the directory of the pyramidal cell. Okay, so I've got all my double underscore Python magic nonsense. Don't worry about that. Oh, look at this. I got a cell.all, I got an apic, an axon, a dend, and a soma. And if I were to look at, oh, these are going to be mildly ugly because of reasons. That's okay. We might learn something here. If I were going to look at, let's just say, the soma sections, I'm going to have a bunch of nonsense, but then there's one soma section. Soma 0. If I were to look at the apic sections, there's a bunch of nonsense, apic 77, apic for apical, right? There's a whole bunch of, there's what, 134 apical sections. You'll notice, by the way, this is a mildly ugly name, though. Main pyramidal object at blah, blah, blah. All right, so my Python experts here. So this is just straight up coming from the name of the Python object. How do I get a better one? How do I get a better representation of this Python object?
Right. Hold on. You want a better representation of that section?
I don't want to see this, though the section part's nice, right? But the part that tells me which cell it is not the prettiest thing in the world. I mean, maybe you disagree. Maybe you think it's pretty, but
does it come from the representation, the matching method?
Absolutely. So it comes from the representation. So if I were to look at PYR, where'd it go? If I were to look at PYR, that is the representation. So if I wanted to do something better, let's say define representation of self, and I will return, oh, you know what I'm going to do? I'm going to go ahead and give this a GID, a unique identifier for my cell. I don't have to do that, but it'll make my life happier. All right, and then I'll return, let's say that this is pyramidal GID. Nope, that's a lie. Self.underbar GID. So now if I were to use this, and I were to look at that, oh, for God's sakes. Oh, because I didn't specify a GID. I've now made it so that I'm required to pass in a GID. So, okay, fine. I want pyramidal cell 0. Let's look at what pyramidal cell looks like now. Now it prints out as pyramidal cell 0. Okay, this is promising. So if I were to look at pyramidal cell's apical sections, it's pyramidal cell 0's.apic whatever. Well, that's nicer. Does it mean anything? Not really, except it'll make a difference for you when you're trying to debug something, if things have good names versus bad names. Because if I'm giving something, you know, the other name is like this auto-generated stuff based on where in memory it's stored, so every time it runs, it ends up in a different location. Good luck trying to debug this. If I give a number and a unique identifier, oh, it's that cell. That's the problem cell, because it's always going to show up the same. Does that make sense? All right.
Yeah, a lot. Robert, sorry,
Yes.
can you plot this particular notebook because I didn't know this kind of tricks in Python?
Can I do what with it?
Plot this Jupyter.
Plot.
upload to?
Upload, yes, yes, I will upload all of these.
Thank you.
Yes. I will put them in the code folder in the notebook. Possibly not until after dinner, but I will do that.
Thank you.
Okay, so we've got our cell. It's got sections. For kicks, let's go ahead and make a pretty picture. So it's with a plot shape. We're going to pass in false. We're going to hopefully not mess this up again. There's no variable that I need to plot, so I can just plot this on Plotly. Have I imported Plotly? Well, we'll find out. And then I'll do .show because I learned. Let's see what happens. If you're running locally, it'll run faster. We're paying $0 for this thing. Okay. The default color scheme is not super great, but there it is. Right, there's our cell. Oops. It's very, let's see. How do we, oh. In any case, it's there.
Is there a way to get the radii? Like plot as a mesh or cylinder? Just curious.
Not inside of Colab. If you're using the traditional neuron interface with a thing called interviews instead of Python graphics, then yes. It's a show diameter flag, but I've never gotten around to implementing it for Neuron. However, there was discussion about if people want to make NetPyNE projects, their NetPyNE project be something that improves the functionality. I am absolutely happy to talk to you about this and how it is that this works. It's one of those, you know, I'll get around to it someday, but if you get around to it first, that will make me sad.
It's not super efficient, you know. I mean, if you only plot a single cell, it's probably fine, but you know, the WebGL has its limits.
Yeah.
Is it just the Google Meet, or is there a break in the neuron?
I'm sorry?
Is there a break in the neuron?
Yeah, so here's the funny thing. You've actually highlighted the exact issue that we're looking at here. So this is the soma. The soma has a diameter that's very large, but we're not plotting the diameter. We're just plotting the centroid.
And it only has a single point.
Yep. So that's what happened here. So there's not actually a break in the neuron. Again, the interviews graphics do better at this. But they don't use WebGL, so like, you know, you win some, you lose some. But again, absolutely happy to talk to anybody who wants to take this on. I don't think it's a hard thing.
No, just I mean, you could minimally just add a sphere, right? It doesn't.
Yeah. All right, but let's pretend that we didn't notice the break at the soma. It doesn't mean anything, right? It's just plotting the centroid. So okay, so let's say, so right now we have our cell, but it doesn't do anything. So I'm going to want to give it some ion channels. All right. So I like to, again, I like to say this as self.add channels. I don't know. And then so everything's kind of self-documenting, right? Like I know which parts are doing what. Add, what do I call it? Channels.
Could we, in theory, also just, you know, after instantiating the class, do add, basically insert the HH into whatever, per.all?
Yeah, and that's in fact exactly what I'm going to do. H dot.
Oh, okay.
Well,
sorry, never mind then.
H dot. So I actually gave instructions that are slightly different. I said I didn't say to put HH everywhere, but let's suppose that we do this. So it ends up being self.all.
Mm-hmm.
Okay. So I've now got a thing, and now my pyramidal cell has ion channels. And if I wanted to know if that was true, let's say that I take the 0th apical dendrites, as good of a one as any. Okay, it has the name, the .apex 0. Cool, cool. And now I can do this p-section method. What p-section, I didn't talk about this, but I'm talking about now, so you know something the other people don't. What p-section does is it says the properties of the section. So here's what we have. I do p-section, and it returns a dictionary, and it just tells me a whole bunch of stuff. It's the axial resistivity is 35.4. The cell is pyramidal 0. That's the actual object. If you were to grab the cell, you can manipulate it as the object. It has a density mechanism, Hodgkin-Huxley, which has various properties. These things are lists because you could have, right now, INSEG is 1, because I haven't said anything else. But if I said something else, then that would be there. Blah, blah, blah. Here's the 3D points that it goes through. You know, this gives us a whole summary of, this is what there is to know about that one cell, or that one section. In particular, the important thing is it has Hodgkin-Huxley channels. So that's a good sign. Oh, you know what we ought to do? Let's discretize this guy. Self.discretize. Mumble, mumble, yes, I will do d lambda. But because I still obviously haven't taken the time to look it up. It's like 3 lines, but why memorize it if you can copy paste? Okay. But so what I will do is I will say this. So for sec in self.all, which is all the sections, I'm going to set the nseg to be 1 + 2 times sec dot the length divided by 40. Right, does that make sense? Yeah. So this is roughly. Oh wait, sorry. So that's silly because math, right? 2 divided by, I could combine that, but the reason that I want to do that is I want to just truncate it. So what this is going to do is if I have something, it's always going to be at least 1. It's always going to be odd. And roughly speaking, every 20 microns is going to give me a segment. I've got these 3 things. This is this is what I've internalized. So, and like I said, this is a reasonable thing. But again, you could change it, right? You want to increase the resolution. Okay, fine. Just change the number and see if it's converged. If it doesn't change, when you change the resolution by a factor of 3, let's say, you're good. It's an empirical test. Why bother doing math if you can prove that it's converged already? Maybe it could have converged faster, but don't care. So, okay, so I've discretized this sucker. All right, and now I have a cell, and we'll notice, okay, fine, it still has length. It still has thing of 1. But in principle, some of them presumably are more than 1. Actually, let's just do this. Sec.l for sec, nope, sec.inseg for sec and pyr.all. Cool. So we have some things that have 1 segment, some things that have 3 segments, 5, 7, 9, 11, and the grand winner, 27. I'm going to assume that's the axon. But I don't know. We could find out, but we don't really need to. But in any case, the point is it's not uniform. So that's a good sign.
Wait, why does it only have, was it like 7 segments?
Oh, so the curly brackets.
Oh, it's a, sorry, it's a set. Yeah, sorry. It's late, it's 11:30. My brain is mush.
Yeah, no, I commend you guys for hanging in there. You know. But yeah, so curly brackets set. But in any case, so we've got our thing. Let's make it go. Okay? Because we've got everything else, I think. We just have to make it go. So, yeah.
Oh, just maybe sort of a follow-up question. So one of the reasons why I'm sort of chasing you up on the, how do I figure out what the optimal number of segments per section is that number of whatever, 20 microns per segment, something sort of specific to mammalian neurons? Because, working with insect neurons, they're way thinner. And I wonder whether I have to sort of account for that by decreasing the number.
I mean, so again, my answer to you is the actual. I mean, the ultimate truth is whether or not you've converged. And so what you do is you run it at whatever you think it is. You multiply it by a factor of 3. Do you get the same results or do you not get the same results? Anything else is I mean, there's a theory behind the d lambda rule based on the AC space constant and blah, blah, blah. But if it either is converged or it hasn't.
Right.
And that's the ultimate truth. All right. So to make it go, what did I say how did I say to make this go? I mean, it really doesn't matter, but I didn't give a specification. How do we want to make this guy go?
I mean, given that I'll go to bed in 15 minutes and I want to see a synapse, I would suggest.
All right, so synapse. All right, let's make a synapse. So we'll add a synapse here. Let's just go ahead and make it a part of, well, no. Let's not make it part of our cell. But let's, we could have made it a part of our cell, right? A cell could have a synapse somewhere. But let's say, so I'm going to have a synapse is going to be an EXP syn, let's say. And I'm going to put it in my pyramidal cells. Let's just put it in the soma. The biologists can complain if they want. Oh, that's a minor detail here. The soma is actually a list of length 1, so it's that. Okay, fine. So I have a synapse. What do I need? So that synapse is going to have a time constant. I don't know, 5 milliseconds. That's a time constant. Different synapses have different time constants. An exponentially decaying synapse is one very simple model of a synapse. There are people who build complicated models of synapses. You can find those on ModelDB and use them. But for our purposes, it's going to be well approximated by that. We'll give it a reversal potential of 0 millivolts. So that's an cytoid synapse. We're going to, yeah, go ahead.
I'm bombarding with you with questions, but while we have you, I think I'll just
please
take my chances. Do you know whether during the course there will be some sort of overview of the different models, whatever channel synapses that are available? Because I feel like this is sort of one of the things where it's really hard to get from the docs, just reading the docs itself, right? Just sort of getting an overview of, hey, you don't know anything about the synapses you need to use, but here are all of them. And these are the most reasonable ones, and then you can start from there.
Yeah, so I doubt it very much, and I'll tell you why. So what NEURON's philosophy has been in general to not play favorites. Okay, so in the sense that Hodgkin-Huxley is the classic, it's the Hodgkin-Huxley channel. But it's not, in particular, it's not even the squid channels, it's the Hodgkin-Huxley channel. So we're not saying that that's how squid act, we're just saying this is how the Hodgkin-Huxley channels go. And so, like, is this an A current? I don't know, maybe it is, maybe it isn't. Because different people have different representations. But I'm going to show you a couple of things. So if I were to go and pick a model, so modeldb.yale.edu, if you don't know about it, we alluded to it all over the place. But ModelDB has I don't know, about 1,700 or so published computational models. They're not all NEURON, but many of them are. I can do a couple of things. So I can go into the folders here, and I can look. So this is a model from Tom Morse, was the first author of Alzheimer's and preclinical Alzheimer's in a single cell. Cool. And in particular, it's got all these mod files, and I can look at this. So here's h.mod. I said, there we go. Here's h.mod. 20 clicks, and it actually registered. In any case, there's some kinetics, and this is a hyperpolarization activated mod file. Somebody mix tabs and spaces. Don't mix tabs and spaces. But in any case, right, so here's our equations. But I can look at this. You'll notice that some of these things have stars next to them. And if I were to click on one of these stars, CAGK, well, let's look at CAGK also for that matter. So it's a calcium-activated potassium channel. Cool, there's equations. But because it's got a star, I know that this exact file has been reused in, I don't know, 10-ish other models.
Mm-hmm.
So that gives me some information, at least, about the suitability. What other people have thought this was suitable.
Fair. And I assume that this is, the other one with asterisk, they've been used in combination, right? Because, what I also don't know is whether, if I want to pluck something out of this model, do I have to basically take all? Do I take, just a couple of them, mix and match? Probably not, right?
People do. I mean, so we're moving into a world where there is more and more data on an individual cell. So like the Allen Brain Institute and the Human Brain Project are doing these things where they're doing tons of experiments on individual cells. And then we know facts about a specific cell. And that gives us good characterization. But it really historically hasn't been that case. We don't have a whole lot of data, I mean, especially on human cells. Non-pathologic, most of the human cells that we do have are because somebody has a pathology or died. And both of those things have implications for the health of the cell. So the other thing I want to point out, by the way, so for all of these mod files, there's an IC genealogy link. It's the ion channel genealogy, which is a tool. It's a collaborative tool with out of Oxford. Tim Vogel's led it. But in any case, so this is basically what happened is he had a grad student, and he made the grad student go through all the literature and track down every piece of metadata that he could about these ion channels. And so apparently this calcium, the data for this comes from a rat, was originally with the CA1. So is it applicable to mouse CA3? Maybe, maybe not. You've got to look at the data that you have to see if it's consistent. They did some standardized experiments of the sort that I was trying to get you to do with exercise 2, which is the voltage clamp. So what's happening here? I'm not really sure. They normalize things, so I'm not. You'd have to look at that paper to figure out how to interpret the normalization. But in any case, there's metadata, there's information. This is a temperature-dependent ion channel. Not all ion channel models are temperature-dependent. And then you can go and you can do this open in channel. What I clicked was open in channel browser. And so they have used statistical methods to cluster the various ion channels. So here was the one that we found, but it's very similar to the one from ModelDB entry 101629 and so forth. But here's a different cluster that's from 2488, which I think is, oh yeah, Mann and Sanowski from a long time ago. But so in any case, you can use ion channel genealogy to sort of look at clusters of different cell models and try and figure out what the fundamentally different types are. That's one tool that you might use. And like I said, Channelpedia exists for the sole purpose of providing channel descriptions.
Yeah, well, I guess it's a start, and it's obviously complicated, so I appreciate it.
But I mean, the problem is people don't agree, and so NEURON generally made the decision, if people don't agree, we're not going to pick a side.
Sensible.
But there's, like I said, there's a gazillion of these things. So every single thing in ion channel genealogy has a ModelDB entry associated with it. They're all NEURON files. So you can just go find something, go there, maybe do some of the experiments. When this is all over, some point later tonight, I'll post in the code folder my solutions to exercise 2, which is voltage clamp experiments. So you can see, does your voltage clamp model of this channel match what your experiment is that you're basing everything on? So you'll have code for that. That's probably about as good as I can do. Can we? Should we go back and get an actual potential and call it a night?
Go for it. I'll just shut my mouth now.
No. All right. So I've got a synapse. Since I don't have a network, I'm just gonna create a fake start, a fake signal to get it going. So I can do this with an h.netstem. And what I'll do is that netstem has a number of spikes. Well, I only need one. I don't need any noise. So that's false. What else do I need? I need a start. Is that right? We'll find out. Nope, that's 5 milliseconds. So, okay, didn't yell at me, so those are probably all true. Again, it's programming. If I make a mistake, I go back, I fix it. No big deal. But okay, so I have one stimulus. It's deterministic. Gonna start at 5 milliseconds. All I have to do is connect that stimulus to the synapse. So let me go ahead and do that here. So I'm going to create a netcon, h.netcon. It's going to go from my synapse. Nope, it's going to lie. It's going to go from my stimulus, my presynaptic. It goes pre-post, okay? Netcon pre-post. Makes sense? But there you go. So it's going to do that, and it's going to have a certain weight. I don't know, 1. Yeah, go ahead. So the weight here, if you recall from the formula for the EXP-sen, is how much the conductance gets incremented. And so the conductance is in nanosiemens. I don't know.
And sort of in practice, like how much do you vary this? Like what's the basis of saying, well, let's say, I've got a strong synapse and a weak synapse. Is that the difference between 1 and 2 or 1 in 100? Or is this one of those questions where NEURON doesn't take sides?
So that actually has an answer because these things actually mean something. So if I go to let's see. All right, so EXP-sen's code here. So the weight is the increment in microsiemens of the conductance.
Mm-hmm.
So like that's actually there's a physical interpretation. It's not an arbitrary number.
Right.
I'm a mathematician by training. I love unitless things, but this has a unit.
I mean, that makes it easier to interpret. So in that sense, it's a good thing.
And this has no delay because it's a fake input anyways. So then let's run it. H.f initialize -65 millivolts, and I'll continue run. When does my stimulus start? My stimulus starts at 5. So I'll run to 7 and see what it looks like. I don't know. It's an experiment. Nice thing about this is we can always go back. We can run it less. Can't do that with a real cell. So I don't have to be conservative. I will say that I want to plot the variable v, and I'll plot the scale from -65 to, I don't know, 20 millivolts. Let's see what it looks like. Does everybody follow me more or less what we did here? We had the cell, we'd had the thing. This is not quite following the instructions because we put Hodgkin-Huxley everywhere, but that's great because it's going to want to fire, right? Versus the one that I had, well, had mostly leak. So anyway, so let's see what it looks like. Oh, the suspense. If you were running local, again, this is the This is the downside of paying nothing for something.
I'm sure they're collecting data.
Well, okay. So you are paying with your neuroscience thoughts. Hello, hi, computer, do the thing. This is there we go. Okay, so that may be that guy really wanted to go. But we can look at this, we can see, let's see, at the center of this, you know, so near the apical, -6. I'm guessing, well, I don't want to wrap my head around this just yet. But it hasn't gotten all the way out to the tips of the dendrites. But it is pretty high. Let's back up because we can do that. We'll run this just to 6 milliseconds, and we'll see what it looked like at 6 milliseconds. And this might be, well, we'll see how long it takes to actually start.
Do we expect it to spike from just a single synapse?
If I hit it hard enough.
Are we hitting it hard enough?
Apparently. I mean, so this is I think this is actually a reasonably large weight for the cell. I defer to the biologists, of which I am not. But I think this is actually a rather large, rather strong connection. By the way, so NEURON obviously supports. So some more complicated synapse models include rules for, you know, LTP, that sort of thing. So this is all stuff that the computer can do for you, adjust the weights as appropriate for a network. But so here we go. So at times 6 milliseconds, we had put Hodgkin-Huxley everywhere. So we've got some high values near the soma. Actually, the highest, though, is a little bit out. It's already started to move. It's already started to drop near the soma, presumably. And it hasn't even gotten out to the tips of the apical yet. If we wanted, perhaps the right thing to do would be to also, just out of curiosity, let's just say I'm going to go ahead and record a few things. Everybody wanted me to record stuff earlier. V soma is h.vector record, what is it, pyr dot soma of 0 of the middle, let's say, dot underbar ref v, and then I'll record somewhere else at the far apic. Well, here you go, apic 25, right? It's kind of pretty far out there. Apic 25. So v apic 25 is 25 apic. Cool beans. Okay, well, that's going on. I'll figure out how to plot something. So from what, import? No, import plotly. Come on. Import plotly.graph objects as go. Fig is go.figure. Fig.add trace. Go.scatter. X equals T, Y equals V soma, name equals soma, fig.add trace, go.scatter, X equals T, Y equals V, apic 25, name equals apic 25, fig.show. Did I do that right? Probably. It is mildly frustrating. It takes a fraction of a second to do the simulation, but with Colab and the Plotly, it's a little sluggish. to load the graph.
Excuse me, may I ask something?
Please.
So we have morphology in one type of file, and we have information about ion channels in a different type of file. And is there any systematic way to know which channels to add to which part of your neuron? I mean, how many channels, which types of channels, where should I take this information? I mean, in a systematic way.
Which channels and the type of channels? The literature. I mean, so I don't know. Does anybody have? I don't have a great answer for you other than saying the literature and other than saying what's present in what cells. So I will say there's this thing called, and okay. So if you go to, we're in the process of redoing ModelDB. So the future URL will be modeldb.science. And if you go here and you look at, let's just say, a CA1 pyramidal cell. Is this useful? Top currents studied with a hippocampus CA1 pyramidal cell. So this is telling us, well, 74 of the models have a delayed rectifier potassium current, 73 have an A current. So you can at least see what's been done in other models. You can see what's been done, but really it's a question of, how do I want to say this? It's a question of what your representation is, and the more what you don't want to do is you don't want to add detail for the sake of adding detail unless you think there's a reason for it, because you just introduce a lot of free parameters that you don't necessarily know. I don't know. Does anybody have other thoughts on this? Because I think that's really a discussion question more than.
Nikita, are you specifically talking about to general modeling or to specific modeling? Because for specific modeling, you need to do a lot of studies. There is a paper. I don't remember exactly the name, but they show that, for example, the sodium channel, it has a lot of sodium channels in the axon initial segment, and then it decreases along the axon. So it's really, I'm guessing it's really neuron specific.
Yeah, okay, thank you. I mean, we can discuss it later if we run out of time. So
I will say, so I think Gordon Shepard and Michele Maiori in the early 2000s had a paper that was sort of a review of exactly this, like A current conductances increase with distance from the soma in CA1 pyramidal cells, and that kind of a thing.
Yeah, okay, so basically what's the point to have that detailed morphology if you don't know the distribution of your ion channels? So it's for synaptic transmission or for what? Because, I mean, it's very detailed, but it does nothing without channels.
Well, I mean, I would say that, again, this is an issue of choosing your model and making sure that your modeling assumptions are matching your level of detail. I agree with you, in other words. But on the other hand...
Sorry, just a short comment. Generally, when we import the morphology, in many cases, we also import the parameters of the conductance and channels, everything. The guys, after the import the morphology, doing some optimization, and they create for each section many parameters to represent the electrophysiological representation that section, and reproduce path clamp experimental. Then also when we import the morphology, you also import our electrophysiological parameters too. In the neuromorpho, many neurons has both electrophysiological and morphological parameters.
Okay, I got it. Thank you.
And I will, yeah, I don't remember what I was going to say. But, so, well, I guess we can probably end with saying, so here is our cell. Here is the soma. We see that the soma starts rising immediately at time 5. And the apical, meanwhile, at apic 25, which was pretty far out there. I don't remember where it was, somewhere around here. I don't know. I don't want to try and find it. But in any case, it was pretty far out there. And it's only slowly starting to ramp up as the current reaches there. So that's consistent. It's showing the same data in 2 different ways. But yeah. So, yeah. Marco?
I have one question. What if we have many morphologies? For example, in a data from connectome, we have each cell with different morphology, and also the detailed synapses. In this case, if we define a function, a class for each one, it would be like time consuming, and there is another way to like define a class and don't define the morphology inside the class and then upload the morphology to this class of neurons.
Yeah,
something like
well,
that.
you could do that. Or I mean, so here's another thing. So here is our example pyramidal cell, right? If I literally just added a new thing here, which was like morphology file, and which was just the file name, right? I could pass that over to the load morphology function, and then so it would just be a parameter to the constructor. Does that make sense? All right, awesome.
Yeah.
All right. So like I said, I will post the other solutions to in the thing.
One small question. So when we define a synapses, we define the synapses in a segment of the neuron. I don't remember the same segment of section. I think segment. But in the connectomics data, you have coordinates in the space, like the coordinate of the presynaptic button and the postsynaptic button. So it's possible to define the synapses node from the segment, the sections, if not from the coordinate, special coordinate or something like that?
It's a solid yes, but. So you can calculate. So the punchline is you can calculate the coordinates of all of the points in of all of the segments, and then through that you can map them, because this every segment goes through specific points, and so that means that you can calculate the coordinates, and so from that you can map it to whichever coordinates are closest.
Yeah.
It's
But
a little
a segment,
nasty. I'm not saying it's
a
not
segment is like one line. It depends of 2 points in the reconstructions of the morphology. So the synapses is like in the middle of, or you put the synapses in like, well, a position in between those two points. That's something like that.
So it would depend on. I mean, so that's a choice for you, the modeler, to make. If I was no, I mean, but the naivest thing to do is to map it to, you know, if there's something that goes close, I'd just slam it over to the.
Okay.
That's what I would do without thinking about it very hard.
Okay. Thank you.
Yeah. All right. If there's nothing further, thank you all so much for hanging in there. I know this is quite late for some of you. Have a wonderful night, and I will see you guys tomorrow.
Tomorrow. Thank you,
Thanks for the
Robert.
demo.
much.
Tomorrow.
Thank you.
Thank you.
Good night.
Bye, guys.
Night.
Robert.
Thank you. Bye.
I don't know.